So yeah, we learned some cool rules. We learned that, okay, we can start counting. We can count these little basic operations, how many steps of execution to make something happen. And that's going to be the same across all of the different processors we could ever want to run our code on, which is lovely. Usually there's a number involved, and so you can kind of see like how much more effort it takes for a bigger size problem. That's wonderful. That's beautiful. And that's useful to us. We learned some simplification rules called big O notation, where we take the highest order term once we've come up with that count, and then we drop any constants out in front, because it really doesn't matter within the same category. We care about comparing to different categories. That's kind of the goal. Like, we learned about the mathematics behind it as well. But yeah, I think that's more or less what I wanted to say. Where was I? We learned about linear search and binary search, and they're like how we know now that binary search is significantly faster than linear search. So that's beautiful. And then yeah, I think it's time for me to start us with a question then. So we learned a bunch of stuff last time. I want you to try this all over again. Please, after you've done attendance, get into little peer instruction groups, say hello to the people sitting next to you, and go look at the slides from last time if you need to. They're up there. That's the same ones that we're using today. And yes, you guys can post your answer on the written ice page that I've just cleared out. So please take a moment to determine the running time complexity of this code. So like, if you need to, you can count the steps, but remember that you're going to do the process of, after you've got the steps, take the highest order term, the thing that's going to grow the fastest, and then you cancel off any constant factors out in front. Okay, so that's my question to you. Give it a try. Does it make enough sense? All right, go try that. And we will figure it out together at the end. No, it is not yet. I'm just saying. I'm thinking. I say. Yeah. Oh, maybe don't go to the slides. Our voices seem to be dying. I'll give you another minute to discuss and enter in what you're thinking. Ooh, that's cool. Yeah. It's still Halloween. I'm not the IT people. I cannot help. Try a different computer, maybe. Sadly, they've locked these computers off. They took the way. There used to be a key in this room, but I can't get into them anymore. So we need the IT people to come and help. All right, I think that was my time. Are we confident? Let's see. Ooh. Some of us think O of n, some of us think O of 1. I guess if you looked at the slides, maybe you shouldn't have looked at the slides because the answer's on the next slide. But let's count the basic steps of like what's going to happen here. What did I call it in this class? I called it, dun, dun, dun. I think I just said steps of execution, right? 1 step of time. How many steps? All right. How many steps does it take? Let's count. Inside the processor, we've got, all right, This line happens once. And then we've got single assignment, so there's that. We've got, and then all of this, when there's no curly braces, the one line below is the body. And this is all going to get repeated how many times? 10 million times, it seems. So there's that. And all right, so 10 million times, we're going to do this comparison. I plus plus is I equals I plus 1. So there's an equals and a plus, like assignment and a plus. And then C out of a couple things, right? C out I itself and then a new line. Those are two separate things. And so all this is going to get repeated 10 million times. So we got the first thing, right? This thing, 10 million times, how many things are getting repeated? 1, 2, 3, 4, 5. So what we got? So this first one is 1. 1 plus 10 million. Dun, 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 times 5. And then we also need one more of these comparisons to notice that we're done, because I will get to be exactly 10 million. And we want to finish off. Notice that this is false and break out of the loop. Plus 1. Are there any variables in this answer? No. There are not, interestingly enough. And so all this is a very large number, but a constant number, times 1. Isn't it? And so, all right, get rid of that constant. So this is, in fact, O of 1. Crazy. Constant time. Still going to take a while, right? But technically, no matter what, it's always going to run exactly that many times. It's always a constant. Does that make sense to us? Constant does not mean fast. It does not have to mean fast. Sometimes it does. A lot of the time it does, but not always. All right. If you have some long run or anything, like it's always going to take that amount of time. It's always going to take a constant amount of time. That's all it means when you say constant time. It does not depend on anything. It takes as long as it takes. Okay. So yeah, that maybe you want to try and find a smaller constant even if it's constant time. So that's the goal there. That's fun to think about, I hope. Questions about that now that we know the answer? All right. And then, yeah, we learned about the mathematics of big O, but honestly, big O just means upper bound. Remember that. So like if you calculated like this is your number of steps, it is all of these things. It's big O of n, because big O, that calculation just means like, can you find a constant to put out in front of this function? Sure, I can put not a 5, but I can put a 6, right? I can say 6n could be my function. And then that will dominate this one eventually. So that would work. This is the best one. You could also say, though, n squared. N squared is totally an upper bound to this function after a while, right? Same with 2 to the n. Still an upper bound to this function. Big O just means upper bound, but we always want the tightest upper bound. All right, that's kind of the goal. So like 5n plus 3 and O of n, those work out because like here's the original function. And then eventually, like some constant times n, 6n, this graph, eventually wins out after a certain point in time. That's all that big O means. Up to a constant factor after a certain point in time, it wins out. All right. So that one's the best. That one's the tightest bound. But like it works for the other ones, like 5n plus 3. Like n squared is eventually going to beat it, right? Same with 2 to the n, right? You got this one. The plus 3 kind of lets it win at the start. But like eventually, that thing is going to go way up. So that's the other two graphs. But we like this one. It's like it's telling us the most information. Like it can't be any smaller than that, right? Can't call it constant because a constant number does not always upper bound this graph. Okay, so that's all the big O means, just upper bound. But we like the tightest bound, we say. Does that idea make sense to us? If you just follow the rules of the boop boop, you will get the tightest upper bound, which is what we care about. Okay, so you get the most information when you say it that way. And now I'd like to teach you some competitors to big O. So this is just something that like determines how fast something grows. Big O means upper bound. There's other symbols that mean lower bound and stuff like that. So let's talk about the others. So really, instead of big O, it's secretly the Greek omicron or omicron. I forget how you pronounce that letter. Tell me if you know. But this one, we got other Greek letters. We got big omega. All right. Big omega is, again, the same idea. Like go back to this page. Like f is big O of g if some things are true. Some function f is big omega of g if some other things are true. Big omega is trying to be a lower bound. All right. So still same stuff. Like F is big omega of g. If you can find some constant c greater than 0 and a constant k such that your function f is bounded below, see, it's always bigger or equal to, this one's smaller or equal to, by your g function multiplied by an appropriate constant. So stretch it a little bit if you need to bring it maybe down, and it's always going to lower bound it after a certain point in time. So if you say f is big omega of g, it means that f grows at least as fast as g, probably faster. It's a lower bound. Okay, so here's this silly little graph. Dun, dun, dun. Boop, boop, boop. This time we do it backwards. So n squared is big omega of 2n plus 20. Does that make sense? Because that's the smaller one. So after a certain point in time, boop, 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 call that k, then your function, if you can scale it by a factor if you need to, like 6, 5, or I guess 1/2 or something if it needs to be smaller because it's a lower bound. But scale it appropriately. After a certain point in time, it should always be smaller or equal to your graph. So that's the perspective shift. This one is now the lower bound, so n squared is big omega of that guy. Does that make sense? It's just the other way around. Just the other way around. We're looking for lower bounds this time. And so play a similar game. Is like, all right, think about it. Pretend that this wasn't just n squared. So it's like 2n squared plus 7 or something. That is big omega of just n, if you think about it, because like this is a slower growing graph, right? After a certain point in time, this one will be smaller. I think forever it will be smaller. If you did like a minus here, then you'd have some trouble. But that's kind of the idea. Okay, so this is a lower bound. N is a lower bound. It's essentially the same graph, more or less, right? It's something below. This one's below it. It's a lower bound. You can also say, though, you can give a tighter bound if you need to get closer. This function is also big omega of n squared. Because if you draw both of them, usually care about positive numbers, can't have negative sized inputs, then what's that one going to look like versus, I guess n squared is probably always going to be a little bit smaller, something like that. Like it's always a lower bound, right? That's the goal. Any questions about that? So I'm not going to like test you on all these mathematical ideas, but this symbol means I've got a function. Here is this function inside the parentheses is a lower bound to that function. Something below it, right? It could be at the same level, but it does not have to be, all right? Does that make enough sense? So big O versus big omega. Big O is the upper bound. We're saying something's an upper bound. Big omega is like something's a lower bound, all right? It's the other side. It is a little weird. And then finally we have big theta, and this is honestly the one you should care the most about. Big theta is big O and big omega at the same time. When you have both, you get big theta. And the definition is pretty much saying that. All right, so I want you to think of it this way. The mathematical definition does not explicitly say that, but you can infer it. So big theta is equivalent to big O plus big omega at the same time. It's the only one that they share. All right, it's the only one they could possibly share. It's like you're sandwiching your function in between this thing g. So f is big theta of a function g if you can find two constants. You can scale g by a little bit or a lot of bit, two different ways potentially. And when you do that, after a certain point in time, k, then your function f is sandwiched by both of those versions of that function g. The one that's squished down maybe by c1, the one that's squished up by c2. It's always between it at that point. All right, and that's what it means to be big theta. And it's the same function, just off by a constant. It's wrapping around it perfectly. It's never letting it away. Okay, so that's saying that. So this is true, right? At the lower end and the upper end, f of n is between them. Okay. Once you get past this starting point k, where it could wiggle around before then, but after that, forever. It's always held between. All right. And what that's saying is that f and g, they grow at exactly the same rate. Just off by a constant a little bit, all right? That's beautiful. And so honestly, when people say big O, they're just kind of being lazy because it's one less syllable. They really are saying big theta. Anybody says big O, unless they're talking about they really care about the mathematics and there's a test on that or something. Anybody who's anybody is, when they say big O, they mean big theta, because that will give you the tightest possible bound. All right, that's what you're getting. All right, so this is your upper. It's an upper bound and a lower bound at the same time. That same function, upper bound. So that's the big O part, and then the big omega part is here. Lower bound. It's the same. It's the only way. It's the only function that you could use that gives you both. All right, that's the goal. So let's see here. For example, we had our, what was it, 5n plus 3? That was our answer from before. What do we want to do? That is, for sure, we know that it's the tightest bound is big O of n, right? Which means big theta of n is the answer here. So this is big theta of n. That's how you say it. It's like, that is the function that bounds it perfectly. You can telescope it in between. And, all right, all we need to do then is find some constants. We can prove this. We can show that this is true if we find some constants that we can multiply by this n to make a graph that grows above 5n plus 3 and make a graph that goes below 5n plus 3. That's all we need to find right now to prove that it is big theta. All right. So, okay, I think we can choose probably 6n, right, as our upper bound. That could be the constant. Upper bound. And we could probably choose 4n as our lower bound, yes? Those could be the appropriate constants multiplied by this n that bring us in between. So at the start, maybe the plus 3 is kind of ruining things, but eventually, and happen. Something like that. Okay? That's kind of what's going to go on. And so, all right, at what point in time do these constants win out? So, I don't know, let's go to 100 probably is fine, right? Because at 100, if k equals 100, then 5n plus 3 is giving me what? 503, right? It's hitting that number. Oops. I want to circle it and move it. So at k equals 100, at that input to my little function, 5n plus 3, I will hit 503. And then when I'm using this one, right, at k equals 100, it's going to be exactly 600. Then at this one, it's exactly 400. It's in between, right? This one is in between these guys, and I think we can imagine that it's going to be in between from then onwards. There's probably definitely a smaller number where you could also show that. That's not the smallest possible k, but that's a k. That's a k value, all right? From then onwards, it's going to be in between this graph of y equals n or something like that. And yeah, squished or stretched by an appropriate constant, it is exactly the same. That's what it's saying. It grows exactly at the same rate as your original function, and that's what the mathematics people were trying to use these symbols for. All right, trying to show that functions grow at the same rate, so it works for us. Any questions about this? You kind of see it? So honestly, if you don't care, just remember, count steps in some way. You can just find constants. Okay, this is a constant, I don't need to care. This is another constant, I don't need to care. And then just take take the thing that dominates and chop off any constants. You've got the right answer for big theta. Okay, I think that's what I wanted to say. All right, so we've got a bunch of options now. Big O is an upper bound. Big omega is a lower bound. And big theta is the tightest possible bound. I guess there's multiple answers if you put constants out in front here, but if you didn't, there's only ever going to be one answer. All right, so with that in mind, here's my question for you. All right, here, let's say we've counted the steps. We've come up with this function in terms of x this time, not of n. And I would like you to express the asymptotic complexity of this function f. F of x equals this disgusting thing. All right, using big O, big omega, and big theta, you know that there's an answer that they're going to all share. And so to make it a little more complex, for once, this is the only time I'll ever ask you to do this probably, try to provide a different answer for each of those. It's big O of this, it's big omega of that, it's big theta of that. Find 3 different answers, please. Don't just say the same thing 3 times because you could. All right? Does the question make sense? Try to do it. Try to find a lower bound, an upper bound, and refresh your page if you're on the written nice page still. Try to find a lower bound, an upper bound, and the tightest possible bound, and give a different answer for each of them. Because you know if you play the game properly, you're going to get the big theta, right? That one's kind of set in stone, but try to find something else for the rest. Something different, because you know that one's, oh, you can go bigger if it's an upper bound, right? Go smaller if it's a lower bound. So think about that and ask me questions as you're doing it if you're not sure. Try to enter in an answer, discuss. There you go, and in between parentheses you put there. There you go. So the hint is there's only one answer, only one normal looking answer for big theta. And that's the one where you like find the highest term, chop off any constants. That will always give you big theta, or the tightest bound for big O / big omega. Another minute or so. We'll see what you're thinking. This is not the easiest of topics. Yeah. Is that enough time? Do we think of some answers? Another few seconds to press submit. But yeah, this is one of the more confusing things, and so I can feed you the information, but it's not the easiest thing to get into your brain. So if you can formulate a question about any of this that I could answer, I'd be happy to. It may just turn out to be one of those things you gotta stare at for a while and practice with.
So, what's the difference between big theta and what we were doing for big O before?
Nothing, because I taught you the right way. I taught you how to find the tightest possible bound.
So big O is actually big theta.
Yes, everybody conflates the two. Every single person does. But like I was saying here, big O really just means upper bound. So when you have something, you could have said this or this or this, because it really just means upper bound. Though you've lost a lot of information when you say something like that. Does that make sense?
That's the real big O.
Yeah, that's the real big O. You could you have multiple possible answers for big O and for big theta. Big O and big omega. I guess you have multiple answers for big theta if you start putting constants here, but nobody usually does. That's a good question. Does that answer it?
Yep.
Yeah, any other questions before we look at your answers? Kind of see the same game you could have played with big omega, just like in the other direction. Yeah, let's take a look. Nice, 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 nice. Big O is something. Big theta's got to be kind of in between, right? In between the others. Good. These seem right to me. Yeah, big omega, you could always just put constant. That's always the smallest thing it could possibly be. Nice. Nice, nice, nice. Yeah, these look good. Very nice. All right, so let's see. Let's see. Make sure to do attendance too, by the way. I'll stop that the next time I think about it. But all right, what's if we play the game, big theta is the tightest possible bound. Like which of these is going to grow the fastest? Well, probably not that one. Not that one because I see 14. This one's interesting. Like you got x twice, so it's really x to the fifth times log base 2 of x. Like that's the whole thing. And then there's a constant out in front of that. So you got to keep them both together because the variables are together like that. And so log grows a little bit slower than just tacking on another x. So it's a little bit less than x to the sixth, right? 4x to the sixth, if you think about it that way. And so that means that this one is for sure the dominant term. So you take that, and then you usually just chop off the constants because big theta is going to add in its own little constants anyway. So the answer for big theta, the tightest possible bound, and for everybody else, if you wanted to, is going to be x to the 14. So this answer is theta of x to the 14. That is the one normal looking answer for big theta. I guess you could put some constants out in here if you wanted to, but nobody usually does. Okay? So that's for sure the only answer for big theta. Does that make sense to us? Like that's the only one that's going to sandwich it properly after a certain amount of time. And that's that one. And then once you say that, big theta is defined in terms of the other one. So you know that now, all right, it's also big omega of x to the 14. That's a lower bound. Just use a small constant. It's also big O of x to the 14. Use a bigger constant. Like it can be an upper bound, a lower bound, because that is the highest order term there. Okay? And so for answers for big omega, like sure you could have said x to the 14, but you could have also said anything smaller than that, right? Big O of 1 constant. Big omega, of x to the 13. You could do big omega of x, big omega of 1, stuff like that. Those are all smaller. Does that make sense? So those are going to grow slower, those functions, for sure. And you could find appropriate constants and starting points to prove that that's true. All right, if you wanted to get technical. And then big O, same deal. It's like, oh yeah, sure, it's x to the 14. That is an upper bound if you use an appropriate constant, but it's also anything bigger than the function x to the 14. It's going to be like x to the 27. That's bigger. Big O of 2 to the x. That's a lot bigger after a certain point in time. Not immediately, because the plus 1, 2, 3, 4, right? It's like that versus what for x equals 0. Like it's that versus 1. First, it's going to win out for a while, but eventually it's going to grow way, way faster. All right, I hope you see that. Any questions about that? Those answers? Yes.
So when you're finding like big omega and big O, it's just anything lower and anything higher than theta?
Yeah, that's all it means. That's all the big omega means. You're finding a lower bound. Big O is an upper bound. But usually you're going to care about somebody's going to say the word big O, and they're secretly going to mean big theta. That's really what I'm trying to say. Like that's the one you really need to care about. Get that tightest bound. Yeah. Question.
If we were to do the top row or like omega and the RX and 14, then you have to say where they become the lower and upper bound.
If you wanted to prove that it's omega of something, yeah, then you'd have to start saying that because you'd have to use the definition. You have to say, all right, it is big omega, and I'm going to show you because C equals this, K equals this, and I will show you beyond a shadow of a doubt that this inequality holds for that. I will not. I will not ask you to do that in this class. CSCI 26 is where I would ever ask you to do that. That's where you learn how to prove things. So, yeah, I really just care that you've heard these definitions once. We're just going to fall back on essentially the idea of big theta and big O, but the tightest bound for big O at the same time. All right? But you need to hear these words once so that you know where they're all coming from. This is their origin story. Yeah, other questions? These are good ones. Okay. Yes.
Will we ever have a function where it's like not the lower bound for the entire function, and it's only lower bound for like a portion specified? For example, like upside down like graph, for example.
I see. Like you've got a graph that somehow looks like this. Sometimes it's a lower bound, sometimes it's not. Not in this class, at least. I don't think I'd ever give that to you. I can't even, off the top of my head, think of an example of an algorithm that would ever do something like that. Usually it's just like, you got a bigger problem, you're going to spend more time on it somehow. Either that or it stays constant. That's a great question, though. I cannot immediately think of an answer where that's possible. But mathematically, using these definitions, you'd have to specify something. Yeah. From then onwards, maybe something happens. Yeah. So yeah, that's more or less what you're gonna do. But you know the secrets now. Just like find the highest order thing, chop off any constants, and you're good to go. So you don't really need to keep track of like each individual counts anymore. If you think about it that way, it's like, all right, it's a constant. It's a constant multiplied by n. I can chop that off. Stuff like that. So yeah, that's the end of that little section. We will of course come back and like we're gonna use big O meaning big theta for the rest of this semester. But that's enough for right now, at least. All right. So sometimes you may want to actually use like a little stopwatch and say, how long did my algorithm take on this particular machine? Like this is our server for my company. I want to know how fast it's going to run on that one. Like you can still do that. You can use the CTime library for that. So in the CTime library, which is part of the C library, you have functions that you could call that show you how long something took. There's a function called clock that like you call it with nothing and it gives you back like the reading of the clock inside of the computer kind of. It gives you back its own little clock T type. You call it once, like it looks at the time, boop, it's that. And then you do your fancy function and then you call clock again. It's like look at the clock now and you subtract. That'll tell you how long it took, right, in between, in terms of clocks. But that's not seconds yet, and so there's a constant called clocks per sec in the library that you can divide by to get the actual, like, convert from clock t's to actual seconds. So I've made a silly little example of that I'll just show you quickly. It's not worth typing out. I've already pre-typed it. Look at it. So, okay. What you do is like include CTime, and then you got your clock. You say that's the start time. Clock gives you back something called a clock t. It's just some large integer value. And then in between a call to clock again, right? You do your work. So the time in the world, in the universe has changed in between. It's like you do your complicated thing. If you want to separate numbers in a way that you can understand later, you can put little quote marks, which is kind of cool. You can't put commas, but you can put little quote marks. So this is the same as saying exactly 100 million like that, but it's much easier to read that's 100 million that way. It's kind of cool. And then what you do is like, all right, those are kind of number values. You can subtract start from end and then divide by clocks per sec, but all these are integer values secretly. And so you got to convert one side to a double if you want actual like seconds with decimals. And that's pretty much it. So it's just adding up a bunch of numbers from 1 to 100 million or 0 to 100 million. Show timing. And so apparently it went very fast. It only took 0.38 seconds inside of my puny little laptop. It'd be even faster on your desktop. Run it again. Takes a slightly different amount of time because other programs are running on this processor. But that's one way to keep track of how many seconds it took to run your program. Okay? Programmatically. Usually though, you're going to care about, okay, this is still constant time, right? But how fast really is it? Because it's still a long running thing, potentially. So yeah, that's how you can time stuff. One day you might need this, like call clock twice, do stuff in between, and then to calculate the difference in time, you can subtract the clock amounts and divide by clocks per second to get seconds. But if you want actual decimal places, these are both integer answers. You got to make one side a double with like a static cast or something. And then it will actually give you double division, which is lovely. Okay, so it's a short little section. If you ever care about getting the time of something, that's one way to do it. Does that make enough sense? Not horrible. Now I want to go to fun stuff if we are ready. Any questions about any of that before I completely switch gears? We're still going to go back to analysis. But I would like to talk about recursion because we have made recursive algorithms. They look weird, it's hard to count how many steps they take. Let's figure this out. All right, so I'll just review recursion, and then we'll go from there. So remember that recursion is you're solving a problem in terms of itself. You're finding that same problem in a smaller form inside of itself, and that is beautiful. And it's sometimes the only way to solve a problem. All right. And for us as computer scientists, recursion is like we're making a function. Like that's how we solve things. We're going to make a function, and that function is going to call off to a smaller version of itself. All right. It's going to ask it for an answer and use it to build up its bigger answer. So it's kind of like it's always got to be smaller though. Like your recursive call, when you make a call to yourself, it's called a recursive call. And it's got to be smaller so that eventually things stop. It's like those Russian stacking dolls. Like you got the biggest one, and then inside of that, like you find your smaller doll. Inside of that, you find a smaller doll. Eventually, you get to the smallest doll. Whee! Can't go anymore. And then you've got an answer immediately for that, and you start like stacking them back inside. Like, okay, I can use that one to build this answer, then I can use that one to build this answer, use that one to build this answer, and eventually you can build the original answer for the largest problem that you cared about. All right. So you break down a recursive problem in terms of two different kinds of cases. You can have a base case, potentially multiple, where you know the answer. That's the smallest doll. If the answer is 42, if you ever see me, just immediately give that back. That's the base case. You can immediately solve the answer for your input. And then the other case is the recursive case. Again, there might be multiple kinds of recursive cases, but that's the one where you call yourself. Where, all right, I'm here, but I know that I can find a smaller piece of me. And I can hand off my problem to that. If I get that answer, if I just had that answer, I can build up the bigger one. All right? So that's the recursive case. That's what that's called, right? And you can break down your input into smaller version, a smaller version, or potentially smaller versions of the same problem, solve all of them or the one, and then you get the answer back from you, a smaller version of you, gives it back to you, and then you build up your answer from this, okay? And so, yeah, let me just prove to you, we'll do an example, do a simple recursive example to remember what it looks like, but let me give you the mathematical reason in a hand-wavy way. Again, wait till CSCI 26 to see better answers here, but let me try to prove to you why recursion works, like why you calling yourself will ever stop, like why will ever give you an answer to anything at all. So here's kind of the secret. So let's say we got a problem, and our problem's called P. That's the name of our function. And we would like to solve P of n for any input n. For any number under the sun that's like, let's say it's from 0 onwards. Size 0 problem, size 1 problem. Like we want to call P with any number up to infinity. That's what we'd like to do. So, okay. Here's what happens when you write your recursive program. You break it up into a base case and a recursive case. So the base case is kind of you shouting out to the world, base case, you're shouting out to the world that I know how to solve the smallest version of the problem, P of 0. You show me that, you ever ask for P of 0, I have the answer immediately. I'll give it to you. That's what you're saying in the base case. So that's part of your firepower. You need that. And then the recursive case, looks a little weird. It's saying that if you were to give me, like I'm trying to solve P of n right now. My goal is P of n. Bless you. You're saying that if somebody were to have given me P of n minus 1, a one smaller version of my problem's answer. If somebody gave me that, I could build my version. I could build my answer. That's what it's saying. If I could just use that one to build that, I would get it. All right? That's the other part. That's what the recursive case is saying. If I could use, somebody's asking me for P of n, if I could use this one, if somebody gave that one to me first, I could use it to build my answer, P of n, one bigger. All right? And the magic of recursion is that you get to assume that, like, you're going to make a call to yourself, a smaller version of yourself. You get to assume that you're getting the answer back. Because eventually you will make your way down the base case and build back up, right? So I'm going to show that to you in a second. But you get to assume that the recursive call right here, you call yourself on a smaller input, you get to assume that it works. Go ask for that smaller answer. You really will get it back. Assume it works. You really will eventually get it back. And that will let you build up anything. So like the base case is you doing this. The recursive case is you doing this. It's like it's asking for a smaller problem and using that to build up the bigger answer. Because that really will give you anything, right? Because like you have P of 0 at your fingertips. You have that answer. And then once you have that, you can use the recursive case as like, you give me a smaller version of the problem, I'll build you the next bigger one. I'll build you the next bigger answer. So you can plug in P of 0 for here. Like set n to 1. It's like, all right, you give me P of 0, I will give you P of 1. That's what the recursive case is claiming when n is 1, right? That's what you're programming. And so you can use P of 0 to generate P of 1 using the recursive rule. Does that kind of make a little bit of sense? Like that's what it means to have a recursive case. And then now you have this answer at your fingertips. Now you can play this game all over again. Feed that into the recursive case with n equals 2. And then it's like, all right, if you were to just have given me P of 1, which I have, here you go, I will build for you P of 2. And it will do that. That's the beauty of it all. And so you can just keep chaining that. Now forever, I can build P of 2. Boop. I can build P of 2, stuff like that. I did not want that arrow to stay there. And that's supposed to be a 2. Can't think and talk at the same time. And then, of course, you could use that to build P of 3, like plug it into the recursive case. It'll spit out that for you, all the way to the answer that you really wanted. Do you see how that's going to work forever? Like, first you start with this answer, you have that concrete in front of you, and then you just keep plugging it in the next one that you get to the recursive case. It's going to, all right, you gave me a smaller one, I'll give you the next bigger one. That's what it's claiming. As long as you do it, it'll work. All right, but the recursion, the way that the recursion is going to work, it works kind of backwards. It makes its way down to here, and then it goes and does that. Because like you're originally calling your problem with the original size answer that you care about. It's like, give me P of n, please. What it will do is it will make recursive calls. Like it will go ask P of n minus 1 all the way down to, it will go asking P of 3 for P of 2, for P of 1, for P of 0, and then it finally gets there, and then it starts building up the answer in that way. That's what it's going to look like, okay? Computationally. But to prove that it works, let's just like you start at the base case and just keep building from there. So that's why recursion works, if you cared. And now let me give you some examples of recursion. Are we ready for some examples of recursion? Just to remind ourselves. All right. So let's do the standard few examples that we like to give. Fibonacci, factorial for sure is probably the easiest one, so we'll do that one first. So factorial, do I want... Yeah, why not? Factorial is going to look like this. So I claim, first of all, that factorial is a recursive problem, because like if you look at 5 factorial, 5, 4, 3, 2, 1, always try examples. Do you see how inside of 5 factorial is just chilling right there, 4 factorial? You're always looking for the next smaller one usually. There's also 3 factorial, 2 factorial, 1 factorial, but you look for the next smaller one. And so like you could break it down in that way and say that, okay, yeah, 5 factorial is equal to 5 times 4 factorial. That's one way to do it. And once you notice that, it generalizes, right? Just like for anything, you give me, that becomes your recursive case. It's like, all right, you give me n factorial. I can show you like n factorial then, like extrapolating from this, n factorial is equal to that same n times n minus 1 factorial. See it? And I did not give myself enough room still. That's what that means. N times n minus, I'm just extrapolating from the 5 factorial examples, like set n to be 5. Okay? That's what that is. There's your recursive case. And then you got to figure out the base case. When do I immediately know the answer for a factorial? If somebody gives me and asks me for a factorial, when do I immediately know that answer? Can somebody tell me? What was it?
Factorial 1.
Yeah, factorial of 1. Anybody ask me for the factorial of 1? The answer is immediately 1. Yeah, that would totally work as a base case. You can actually go even smaller. You can say factorial of 0. That is defined to be 1. So that's even smaller. Let's do that one. 0 factorial is defined in math. It makes not a lot of sense to be exactly 1. So anybody comes asking for that one, just like immediately give them that. And that will work for anything now. Any possible factorial you'd want to have, because you can't go smaller than 0. And those become your rules, all right? Those become your rules, and now we can program it. And let me remind you how to program it. So here is that. Let's do fact. We'll call it fact for factorial. Fact of 5, fact of 0, fact of 2. And it's going to be int fact, and it takes some number that's called n. All right? And so to implement this, we got to figure out, like, you do one or the other, right? Which case am I in right now? Am I in the base case or am I in the recursive case? So if n is 0, somebody's asking for 0 factorial, that's my base case. and I will return 1. Otherwise, I must be in the recursive case, hopefully. Unless it's negative, then you have to worry about that. Let's pretend the user is only going to call with normal numbers. Then I need to return my n times n minus 1 factorial. Right? My n times n minus 1 factorial. And the way that you get n minus 1 factorial is, you notice that's a smaller version of the problem I'm working on. I get to make a leap of faith here, like that's how recursion works, and just call myself. It's my job. It's a smaller version of me. Eventually, it will really will make its way down the base case and build up that smaller answer correctly. That's what we're banking on here. And it really will work as long as you do everything else right. It really will make its way down and do everything else fine. So this I can replace then with a call to myself, and this really will become the true mathematical answer for n minus 1 factorial, because it's going to make its way to the base case, build itself back up for the reasons that I drew. All right? Oop, I did not want to call it that. Fact. Cool. And it seems to be working. I see, yeah, 5 factorial is 120. 0 factorial is 1. 2 factorial is 2 times 1. So 2. Perfect. All right. So it really is working. We've seen this example before, hopefully, right? But does it make enough sense how we translated from our recursive case and our base case to this? Yes.
Is it? I'm confused. Is it just, is when they go down to 1 times 1 times 1 times 1 forever?
Forever? Ooh. Well, let me draw the stack. That, I think that's what I wanted to do anyway. Let me show you what it's going to think about computationally. So we've got in main, let's say we called fact of, I'll do fact of 4 because like that's less drawing for me. So let's say we called fact of 4. So main calls fact of 4. I'm going to be lazy and just draw it like that. Fact of 4, even though really I should be drawing it like n is holding 4 or something like that. So that's main calls fact of 4. We're sitting in fact of 4. And 4 is not 0, so we're going to go here. And we're going to try to return our 4 times fact of 3. Yes? Our 4 times fact of 3. We're going to go asking for fact of 3. We don't have that answer yet, so we can't actually return anything. We have to wait. So fact of 4 is going to wait on that line for fact of 3 to get back to it. Send it a little telegram. Wait to get something back in the mail. All right? And so now we're sitting in fact of 3. Fact of 3 is the start of the show now. Fact of 4 is just asleep. Now we're in fact of 3, where n is 3, still not 0, so it's fact of 3 is going to try to return its 3 times fact of 2. That's what its answer will be. But we don't know what fact of 2 is yet, so we have to go ask for that before we can do the math and actually return something. So fact of 3, again, is going to wait on that line and be like, oh, okay, fact of 2, get back to me, and then I have an answer to return to somebody. Fact of 2, and then, again, fact of 2, where n is 2, still not 0. It's going to try to return its 2 times fact of 1. Does not know what fact of 1 is yet. It has to go ask for it. Once it gets it back, though, it can multiply that by its 2, return the answer to the person below it on the stack. Fact of 2 is going to call fact of 1. So all these guys are just chilling on this line right here. They're waiting for the person above them. They need that smaller factorial. And eventually we will make it to the base case just for the same reason as this diagram. Fact of 1, again, 1 is not 0. So we hit the else case. It's going to return its 1 times fact of 0. So it goes and asks fact of 0, hey, what is your answer? It's going to call and wait on that line again. So fact of 0. So everybody except for fact of 0 now, all these guys, are waiting on that same line for the person above them, that smaller factorial. Because only once it gets it back does it have an answer to do multiplication with and then return, right? So, okay. Finally, we're in fact of 0, and it's like, I have an answer for you. I'm the base case. Oops. I am the base case. I have my answer. It's my n is 0. Finally, I can return 1 to whoever called me. There. I can return 1 to whoever called me, and that's just the person below me on the stack. So fact of 0 returns 1 back to fact of 1. And so now fact of 1 is, it saw fact of 0, is calling fact of 0. It sees the 1. It can multiply its 1 by that and return its answer to whoever called it. And now it's done. Does that kind of make sense how we're unwinding? It really is getting down the base case, building it back up. As long as you do everything right, it really will do that. Then fact of 2 is where we were. Fact of 2 is waiting ever so patiently on fact of 1. It can multiply its 2 by that answer once it gets it back. It got it back. Fact of 1 is 1. So it can multiply its 2 by that, return that as 2, which is the correct factorial of 2. Now fact of 3 was waiting for that. It got it. Fact of 3 was waiting for fact of 2 to multiply its 3 by that. And so it sees 2. It can multiply its 3 to make 6. And then it has something finally concrete to return. 6. Now it's done. Back to factor 4 was waiting ever so patiently. On factor 3 to multiply by its 4 to return an answer, it finally sees 6. Can multiply that by its 4, its n, to make 24, and that's what main was asking for. If you called factor 4, that was. We did factor 5, but that's same idea. Does that make sense to everyone? How that's going to make its way down, build its answer up. We're walking through the code. You see it? Convince yourself. Draw that diagram. Stare at it long enough. But that's the secret. That's what's going on. Whee, so that's factorial. Yeah, ready for the next one? All right, let's do Fibonacci. I like Fibonacci. This is going to be 2 recursive calls. That's why we do it. So the Fibonacci sequence is a beautiful mathematical sequence that kind of like exists in the wild. It's like the essence of beauty. Some special number phi that is like present in nature. You look it up on the Wikipedia page. But the Fibonacci numbers are just a sequence. They start like this. It goes 0, 1. And then after that, you take the 2 previous ones and you add them together to build the next element of the sequence. Like 0 plus 1 is 1. You just add them up. Add them together. Boop, boop. 0 plus 1 is 1. And then the next element of the sequence is 1 plus 1. Just like the 2 previous ones. 2. And then, all right, 2 plus 1 is 3. 2 plus 3 is 5. That's the Fibonacci sequence, and it goes on forever. 5 and 8 and 13, stuff like that, right? And that's, you're getting that again from the 5 plus the 8. It's just forever, that's how that works. And let's say that these are we're asking for like the nth Fibonacci number. This is like, I don't know, this is Fibonacci number n equals 0, n equals 1. Like those are the elements of the sequence, stuff like that. This is what n equals 1, 2, 3. This is n equals 3, n equals 4, n equals 5, stuff like that. So that's those elements of the Fibonacci sequence were like, this is the 0th element, kind of, okay? And so if you think about it, like, how did we build, I don't know, the Fibonacci number, what is this, 5, 6, 7, n equals 7. How did we build fib of 7? N equals 6. Do you see how you could use smaller versions, if this is like a call to the function that gives you back that Fibonacci number? Do you see how you could call with smaller inputs to build this answer? What is it but the 6th Fibonacci number plus the 5th Fibonacci number? Yeah? So fib of 7 is equal to fib of 5 plus fib of 6 in any order. Fib of 6. Does that make sense? Like that's what's going to happen. I ran out of room. Let me try to give myself more. But that's one way to generate these. Fib of 6. That's good enough. And then we've got, let's see here. 5 fib of 6. Now we got recursive case and base case. So we've got the recursive case, just in general, like you generalize this. Recursive case is you're asking me for the Fibonacci number of n. That's equal to the Fibonacci number 2 ago of n minus 2, right? That's n minus 2 is that. Plus the Fibonacci number 1 ago, one before me, n minus 1. That's the recursive case. Just read it off. And then there's actually going to be 2 base cases, because notice that you can't run this rule unless you have 2 things before you. So like n equals 0, there's not 2 things before it. Same with n equals 1. There's 1 thing before it, but not 2. So you just kind of have to hard code those 2 first ones. So you got 2 base cases. Fib of 0, define it to be 0. Fib of 1, define it to be 1. Does that make enough sense? And that's what's going to go on there. And so again, we can code that up. Fib.cpp. Dun, dun, dun. Do I want to do that now? I'll deal with that later. So that's that one. Do I want to steal most of what I had, maybe? Let's try that. It's going to look very similar. So here we've got, instead of fact, we call it fib. And let's see. It's going to be most of these things. There's going to be multiple recursive cases that I'll deal with that. Let's do, I don't know, fib of 5. Fib of 0. Fib of 2. Something like that. Let's get those working. So Fibonacci numbers, base cases, it's either 0 or 1. So if it's 0, the answer is 0. Oops. Else if n is 1, so I'm asking me for Fibonacci number 1, the answer is 1. And then this is just else now. Still a recursive case. So what does the recursive case look like for Fibonacci? It's just like I want to return 2 Fibonacci numbers before me plus 1 Fibonacci number before me. Add them up. Calculate them and add them up. There's smaller calls to myself. Fib of n minus 2. So these 2 calls really will get to some concrete thing eventually and give me those smaller Fibonacci numbers that I can use to build up towards myself, all right, to get my final answer. It might take a while, but it'll do it. It'll get down to these base cases, one or the other, eventually, and add up things and give back what it needs to give back. It's a little bit harder to draw the stack diagram because there's 2 different calls, but take my word for it. It will work. Boop. So 5th Fibonacci number is 5. Cool. Then 0th Fibonacci number is 0. Number 2 is in fact 1. So it's all checking out, and that's the code. Does it make sense how we got this code from these 2 rules down there? See the translation? I got one more that's a little weird looking. This has to do with pointers. But it's still fun. So if we are good with it, these are just ones to remember and to get practice with. The last one I want to do is let's say that we're given an array this time instead of a number. Let's sum all the values in an array recursively. So here, let's say that I've got an array, call it R, and it holds some numbers in it. Like, I don't know, 1, 2, 3. Can you kind of see what's going to happen in like a recursive case? Can anybody show me a smaller array to add up stuff in? Because that's your smaller problem, right? You're trying to add up the numbers of an array. Can you find a smaller array to add up numbers in from that one? I think so, yeah. 1, 2. You could circle things all day long, right? It's like this could be a smaller array. This could be a smaller array. If you want to chop off the 2 for some reason, those 2 things together could be a smaller array. You can find a smaller thing, right? And that's a smaller thing to go through. That could be recursive. Does that kind of make sense? So it's kind of like what you want. There's your smaller array. That can make your recursive case, couldn't it? For a sum up all the values function. So like your recursive case is like, my answer is my R of 0. R of 0 plus the sum of that smaller array, and I don't know how to calculate that just yet, but I'll just call it sum of the smaller array. It's guaranteed. You get to assume that it'll work as long as you build up everything else right. So that's your recursive case. And then what should our base case be? When do we have an array that I can immediately, I know the sum of it, of all the values in it? Yeah, that would work. So if I have, it's a little odd to want that, but it's exactly what we need here. It's like the sum, if you try to sum up all the values of an empty array, you know you had an empty array, there's nothing in there, right? Sum 0. Isn't that interesting? So now the question is, how do I code this? The question is, how in the world do I code this? And like, how do I create a smaller array as well? Like, that's a little odd to think about. So we're actually going to need a couple parameters, but let me at least show you how to calculate a smaller array. So that always, like, you can give back a new array somewhere. That's fine. It has to do with pointers, because remember that every array, we're very comfortable with this now from vector land. Every array is just an address. It's like, maybe that's address 100. It's an address of where the thing begins in memory. It's like, if R really is something like that. All right, if that's what R is saying, like it's pointing to that first element, and you can do array looking stuff with that. And so to calculate an array, this array, all you need to provide to represent that array, right? The idea of that array, that's this smaller one. It's really just go to that address where it starts. Calculate that somehow. So that's this one. Like, you just need to find out a way to give a pointer that starts 1 later. Does that make sense? 1 int later, if it's an int array. And so how can you get that from R, because that's what you have? It's really going to be R plus 1. Remember that pointer arithmetic stuff? So plus 1 means go not 1 byte address later, but go 1 int address later. So it's 4 after. So that's perfect for us. But that's how you can calculate the smaller array. You'd be like, int star, it's array of ints, int star smaller array array equals my old original array plus 1. Give them the address 1 later, and then I'll use this as an array, because it is. Let's go to, and now you can go to smaller array of stuff. If I can write legibly. Array of like 42. Like you can go there now. You can use a pointer like an array if it is an array, and it is. It's just a little bit smaller. Does that make sense? That's so cool. And that can be what we use now. That's how you can pass a smaller array. It's like pass a pointer starting 1 later. So that's the representation of arrays, where it begins. Cool. That's a little odd though, I admittedly. But it's a cool example. Was there a question?
I was just saying it is cool.
Yeah. So it's a good one to study, even though it's a little disgusting. So let's make an array. 1, 2, 3, and then I'll see out the result of calling my sum array function that I'm about to make on R. You do also have to pass the size of that array because they don't know their sizes. You got to know when you're done. Int sum array is going to take an array as a pointer to where it begins, and then the size of that array that we're trying to look through. So that's also how we get our base case, because you can't just like, what is the address of the empty array? It could be anywhere, right? It could be anywhere at all. So you look at the size to know if you're empty. You're done. So if my size is 0, then I know I'm finished, but I've got nothing in my array to go through and sum up. So I'll return 0. That's the sum of everything in an empty array. Otherwise, I will, my answer is, what I need to return back in that case is my first thing, right? Because that's what the small array does not include the first thing. I still need to include that. So my 0th element plus the sum of my smaller array. And it's on me to get the smaller array, right? Else return my R of 0 plus the sum of the smaller array. So that's a call to me. It's going to work out. It will make its way to the base case. It will figure things out properly. As long as you do everything else right, due to the magic of recursion. You just got to make that leap of faith. It will work out. All right. R plus 1 gives me the address of the next element over. That's the smaller array right there, R plus 1. And then how big is that smaller array? It's 1 smaller than the one I've got. Size minus 1 is its size. Does that call make sense to us? It's a little weird looking, but that will give us what we need. Whee! And there, yeah, 6. 6 is the answer. Lovely. Any questions about that? This is draw a picture. Definitely try to draw a picture that I can help you. That would be a great way to study. All right. Questions about that one? All right. Because now I'm done writing code. Now let's talk about this. Like, how in the world can we determine the complexity of these things? The easiest way is to draw a little tree diagram that shows like how many things are getting called, and that's probably that's the best thing for this class probably. So your book will talk you through this kind of stuff. What you want to do is you make a little tree, which is something that looks like this, got some branches and some elements and stuff like that. It looks something like that, and it will kind of track how many recursive calls are happening for your input, your inputs of size n. Like draw a little picture. What you want to do is try to keep track of those things. Like you got your tree. Like the first call is calling 3 things, then the next calls are calling 2 things, and maybe those are base cases and they stop. So kind of to count to deal with the complexity, you got to deal with like what's the complexity of each individual call, and then how many am I making? Like figure out how many levels we're going down and like how wide it is, and like then you can do some math to see like how complex it was. Does that kind of make sense? Like figure out how many calls are getting made in picture form usually. Okay, so let's talk about Fibonacci. Fibonacci's weird looking. So like let's determine the complexity of Fibonacci. Like this is pretty much the exact same implementation, it's just a little bit cleaner. It's fib still. More or less the exact same. This does the n-1 first, who cares? Does not matter. Same function, more or less. And so let's figure out its complexity. So like let's say I called fib of 5. How is this going to work? So it's not the base case. It's going to do this. So it's going to call fib of 4 and fib of 3 to build up an answer, right? Fib of 5 is going to call fib of 4. It's also going to call separately once that's finished fib of 3. Does that make sense? Like how I'm drawing that diagram? Because that's the start of analyzing it. And then, all right, what's fib of 4 going to do? It's going to, again, hit this case, and it's going to ask for fib of 3 and fib of 2. And then what are they going to do? Fib of 3 now. What's it going to say? It's going to ask, again, it's not the base case yet. It's going to ask for fib of 2 and fib of 1, right? Fib of 2 and fib of 1. This is the kind of diagram you want to draw. Kind of see how I'm doing that? It's like who's calling who? All right, and fib of 2, still not the base case, but it's going to call fib of 1 and fib of 0. And finally, we're at the base cases, yes? So now these are done. They're going to stop. And they'll hit those. Same with this fib of 2. It's going to call fib of 1, fib of 0. A little weird looking. And then what do we got going on here? Fib of 3 is just going to look like this all over again over here, yeah? So, all right. Take all that, copy, paste. Shove it right there. Boop. And so if we wanted to count, like what's going on, if you think about it, for each call, it's just going to do some comparisons, potentially making recursive calls. We're not going to deal with those. We're going to count those separately. It's going to do some comparisons and return something after maybe having done math. Does that make sense? That's all constant work per call. Does everybody see that? Per call, it's constant work. It might make some smaller calls, though, and we got to count those separately. You kind of see how I'm dealing with that? Like, that's what you think about. That's what we think. And so what are we doing? So essentially, the question is, how many calls am I making here? Just like that, multiply that by 1 for each constant, like by O of 1, and I've got my analysis. All right? So generally, if you think about this, what is this? This is at level, this is the original call. There's only one call at this level. Once you go down 1, you're making 2 calls, yeah? There's 2 calls at that level of recursion. At this level, I think you can imagine there's going to be 4 calls, yes? It's more or less splitting. It's leaning this way, though. It's a little bit heavier on that side, but more or less, it's like 4 here, 8 here. It's not perfectly doubling each time once you get towards the bottom, but more or less, like that's an upper bound, yes? That's an upper bound. So at this level, maybe there's about 16 calls down here. Yes? Does that make sense to us? Because it's doing this recursively. It's doing 2 different things. And so if we had to add this up, it's like, all right, at this level, I'm doing 1 amount of work plus 2 amounts of work at this level, because it's constant work per level, right? Constant work per call. It's like 2 calls times constant work. Plus 4, plus 8, plus all the way down to, how did I get 16 from 5? With doubling involved, 2, 4, 8, 6, it's 2 to the 4, right? 16 is 2 to the 4th power. So that's 2 to the n minus 1, essentially. What was my original thing, minus 1? Does that make a little bit of sense? That's your kind of analysis there, yes? That's kind of what's happening. And so the first level has 2 to the 0 calls to Fibonacci, because it's kind of doubling each time, doubling at each level to the 2 recursive calls. And then there's 2 to the 1 calls at the next level, 2 to the 2 calls at the next level, right? You just want to add all those up. You're doing that n times, so up to n minus 1. And there is a formula for that. The formula to add all these up, you can think about it in terms of binary. If you know binary, it adds up to be 2 to the n minus 1. Does that make sense? That's just, there's math for that, all right? So essentially, like we were talking about, there is constant work done per function call, right? Don't count the inner function calls. Like, all right, assume I have those answers. I'm just doing math, comparing, and returning. That's constant work all around, no matter which branch I'm going down. So there's constant work per call, per function call, and then there's on the order of, right? This is on the order of 2 to the n calls being made, yes? So what we get is, all right, constant work per call times about 2 to the n function calls. Does that make sense? Function calls. And so, in general, like how to combine the constants, that becomes big O or big theta, right, of 2 to the n. Like, that's your analysis. Does that make enough sense? It is a slightly, like, it's a smaller thing. It's still exponential, but it's more like phi to the n, 1.5 whatever to the n. But this is an upper bound, something like that, all right? Does that make sense, what I just did? That's the kind of analysis you do. Fibonacci is a little bit hard. It was easier. It would have been easier to do factorial. But 2 to the n is disgusting. We know that graph is going to blow up, yes? So let's try to call fib of 200. This is another fun thing I like to show my CSCI 40 class, so pretend to be surprised again if you already took my class. Fib. Well, it does all the others. And then that's just sitting there, right? Then it's just sitting there, and I get to tell you, right? Just like try to do the math. Pretend like it takes a millisecond or something to do all these calls. We are kind of running out of time, but just for fun, we can do the math, right? It's like pretend it took a millisecond to run all those calls, which is 0.20 to the, is it -6? I forget. Something like that per call, and we did 200 calls, so it's that times 200, 2 to the 200, right? Because that's how much work we're doing. So it's that many seconds we have to wait, divided by minutes, minutes, hours, 365.25 days in a year. It would take longer than the universe has existed for this to finish. All right, that's the goal here, and I think I've also done that here. So that's disgusting, right? So we'd all be long gone by the time that would ever finish. So I'm going to press Control-C to stop it. So that's fun to think about, right? It would take billions of years, disgustingly. So the last time I checked, this was the fastest supercomputer in the world. It was in Japan. Maybe it's been outclassed by somebody now, but it can do this many operations per second, 4 times 10 to the 17. All right. So even if we ran this on this thing, Fugaku, if we did our fib, assuming it takes 1 operation per fib call, and that's being nice. You did that. You divide by that many operations per second on the thing. It would still take this many years to complete it, and the Big Bang happened, scientists say, that many years ago, right? So it would take a few Big Bangs amount of time, quite a few. Disgusting, right? So we would all be long gone, and this is a disgustingly slow algorithm, apparently. Disgustingly slow. There's another way to do Fibonacci, right? We could do it this way. We can do it as a loop, just like keep the 2 previous numbers, add it in. Let's analyze that. Let's look at that one. This is Fibonacci iterative. All right. Oh, where did I go? Did I accidentally close a tab? I accidentally closed a tab. So this is I gotta call it something else. Iterative. Using a loop, just pretending that the old things. This is O of n. Theta of n, right? It's only doing n work, constant work, n times. And if I call that one fib iterative, or I guess here, that one, comment out fib iterative on 200. It won't get the right answer because it will overflow, like the answer cannot be held in an int, but it will give you an answer, like it will do the work. If you had big enough numbers, like it would have done the right thing. It's like blink of an eye, it figured it out, because it's only doing about 200-ish things, right? It's doing linear time work rather than exponential time work. Does that make sense? Same problem, different answers. One is significantly better. This is why we're taking this class. Yeah? This is why we're doing it. So now we know. Okay? So there's trade-offs to be made. Sometimes the problem can only be solved recursively, but other times, like, you reach for the better one when you notice that you have a better one. All right? And that was disgustingly long. All right? Any questions about that? Does that make sense? And you can play the same game. Try to play the same game for like factorial. You'll notice that it's O of n, because it's only ever going to make one recursive call. Factorial, it's only going to do this, right? It's going down how many times, like n plus 1 times, doing constant work per call for factorial. That is linear still. That is still linear, yeah? So let me, that's more or less what I wanted to say. Let's talk about, finally, space complexity. Space complexity is the flip side of time complexity. It's like time complexity, how long it took in terms of number of operations. Space complexity is like how many bytes of memory did it take to complete the execution of this program, all right? Because all we've cared about so far is running time complexity. Space complexity is pretty much the same idea, though. Once you get one, you can understand the other. So I don't have many slides on it. So space complexity is the amount of space being used by your code. And let's see. Do I want to code any of that up? I don't think I do, actually. So, like, let me just give you some examples on paper. So like, say you made an algorithm to reverse an array. Yeah, maybe you've learned that one before, that algorithm. It's like you've got an array, you'd like to reverse it. You'd like to take it and move things around, right? Maybe it's 1, 2, 3. You want to make it 3, 2, 1, right? You want to flip these guys. I guess you can flip the middle element if you really wanted to, but you don't have to. Like this becomes, you swap things. That becomes a 3, that becomes a 1. You do that for the whole array. Yeah, that's what you would do. That's the in place version of reversal where you're editing the whole array. How do you do that? Well, you're going to iterate, right? You're going to use like an I variable, which is another int. You're going to do some swapping at each element. Like you're going to calculate this index, and like make your way inwards as well. Do your swapping, which is going to take a temporary integer variable, right? That's how at least I say, right? Some other variable, right? And that's pretty much it. You've got your array already, and like you're given the array. Like that's not part of the algorithm. Like you started with that. Like how much memory are you using to do that reversal when you're doing it in place? Just like how much space are you taking up as you do it? Extra, 2 ints worth of space, right? Even if the array was size 1 million, you're still just using 2 ints, more or less, right? And also, I guess you're taking the array as like a pointer secretly. So like there's room saved for that for your parameters, but that's how that works, right? So the space complexity is constant for that algorithm. Does that make sense? It's like 2 ints plus maybe a pointer for the array itself to remember where it was. But the memory of the array, like you started with that does not count. That does not count when you're doing that analysis. So yeah, the space complexity is not as hard. Not as hard as time complexity. Space complexity is about 2 extra ints, right? To do the work. And every int is exactly 4 bytes. You can't mess that up. There's other ways to do the reversal, right? Maybe it's hard to think about it in terms of this way, like we couldn't remember the algorithm just quite. There's another way to do it, right? You can make a new array. You can give back a brand new array that's like in the reverse order. So what would that involve? And maybe like copy back over. Well, let's see. Maybe copy back over it after you've done the reversal. Like it's easier to think about it in terms of 2 separate arrays, maybe. So like that would be this algorithm. You start with R. You start with your array R that you were given. Like you don't count that. You already had it. And it's of a certain size, right? This is maybe, let's say that this is size n. And let me move this down so I can draw more. Let's say that's size n. And another way to do it is like to make a brand new array and just like, it's a bit easier that way. Just like iterate in reverse and add the new elements that you see, right? Then add the 3, then add the 2, then add the 1, right? You need to iterate, so like using an I variable. And then maybe you can like copy it back into the original one in that way, like go through that and then do that. That would be another thing that you could do. But now, how much memory are we using? Yeah, so we started with a size n thing. We like this is the new stuff for the algorithm itself that we made. We made another size n array and plus like an int for your I variable as you went through it, right? So that's about n plus 1 new ints, yes? So okay, do your big theta, do your big O, right? Then that becomes O of n space complexity. You used on the order of the original size of the thing all over again. O of n space complexity. Sometimes there is a trade-off to be made. In place, if you can swing it, that's the best one, right? Because it's linear time, constant space, yes? This one is also linear time, but it's linear space. So it's definitely going to be worse. Definitely worse. This one's better. Sometimes there is a trade-off. Sometimes you do trade time for space. You'll learn about some of those one day. But that's kind of the setup. Does that make enough sense, what we're calculating here? It's like, how much room are we using as we ran this thing? You do not count the original inputs. Like you already had the array itself. Like that's not extra. Like it's not linear space because of that. Like you were given that, you say. Okay? You count the parameters themselves. So like you took a pointer. Like that's how you got past the array. Like that's being used during the call. But that's about it. Okay? So yeah, and then when you're dealing with space complexity of recursive functions, then things get really interesting. So think about, let's do factorial. Like here's the factorial example. Every time you call a function, you are using memory. Stack memory is being taken up to remember like who's below you, like where do I return back to, like that's secretly there. Also, the parameters themselves are taking up space, right? There are a bunch of different copies of like, what was the parameter's name? It was n here, right? N per call, yes? And so how many calls at most are going to end up on the stack at one time? Like fact_4 is going to call all the way down to fact_0. There's going to be n plus 1 calls to your factorial function. Does that make sense? And they're each taken up like an int worth of space per parameter. So they all have their own versions of their n parameter. And so, constant space per call, but you're going to end up having a chain of n plus 1 of them. So that's linear space to use the factorial function recursively. Does that make sense? Because you got all these in the like eventually you're going to have all these for a split second. They're all going to be there at once. You need that much room. They will eventually start whittling themselves down, but you need that much room to get down to the base case. All right. Worst case. Worst case. What's the max? Take the max. So linear space. For fact. And that is not obvious unless you think about it that way, right? Because if you had your factorial function, you think about it this way, oh, it just has an int, one int, and like I'm just returning some stuff. Constant space. No, constant space per call. How many calls am I going to see on the stack at once? You have to now worry about. Okay? I hope that makes sense. So yeah, any questions about this slide? You see it? All right, your turn. This is my last question for you of the day, and then I have a fun little example. So let's please go to the by clicker page. I remembered that I was going to stop that. And let us try one question. I'll let you guys, of course, get into groups. Please discuss, do all these things. But I'd like you to calculate the time complexity and the space complexity of the following code. There's some loops, there's some variables. N and M you were given. So those are just variables with some value. Maybe we got them from the user, who knows? So like you have no control over what these are. So if you need those in your answer, you just got to keep them variables. What else? And then every time rand is called, it's giving you some random number. Assume that the call to rand takes constant time. Okay? And it really will in practice. So that is your code to analyze. Assume that random, every time you call rand, it's just O of 1 every time it gets called. Or theta of 1. And I'd like you to try to calculate the time complexity and the space complexity. Questions about the question before I send you off? The answer is one of those 4 options, okay? I promise. All right, please discuss and try it. Convince your neighbors that you're right. You're not sure which of N and M are bigger as well. You have no control. No control at all. Do we have rid of that? That's so sad. They got rid of that. It was -4. Another minute or so to think about it. Was that, or is that enough time? Can't tell. It's an update. All right, that was my timer. Take a few seconds to select an answer, please, whatever you were thinking about. And then we'll discuss. All right, let's see. All right, we think that it is C with a majority, I think. Awesome. So let's take a look. Let us take a look. Some spam caller is calling me right now. That's all right. We think it's C, and I think the answer is C. Nice. Let's take a look together. So let's do space complexity, or sorry, let's do time complexity first. Then we'll do space complexity. So, well, you're gonna assign some variables, right? You got the numbers already. That's constant time for that line. Yeah. We're just gonna add them up, right? When we got this loop, what is this loop gonna do? It's gonna do that. That's constant time for that, and it's gonna loop its body in the comparison and the plus plus n times, right? Whatever n is, I'm not sure. How much work is it gonna do each time? No. Each time it's, well, a comparison, couple addition and assignment, more additions and assignment, assuming this is constant. So it's constant work per iteration of the loop, yes? But there's n iterations. And so it's going to be, we got constant work times n. And so this whole loop then becomes O of n, or theta of n, yeah? And then more or less the same things happening for this loop. Yeah, it's just m instead, right? It's like this is going to be repeated. This is constant at the start. So the whole loop becomes, like, we got constant work happening m times, yeah? M times from 0 to m minus 1. That's what j is ranging between. And so we've got this one taking up O of m work, yeah? And so if you want to figure out how much time it's taking total, it's like this time plus this time plus this time, because they're all separate, right? There's no nesting, yes? Like those things, add them together, what is the answer? And so we have to give one final thing in between an O, right? O of something. You can't just be like O of n plus O of n, because that kind of is the answer at the same time. It's O of n, because the 1 for sure is going away, right? 1 for sure is small. But we're not sure which one's bigger, n or m. We have no clue. We have no control. Maybe the next time we run it, m is bigger. The first time we run it, n is bigger. Does not matter. What does this really look like when you say big O of things? You know it's like, all right, there was a constant 1 times n, plus maybe some lower order things, plus some constant 2 times m, plus some other lower order things. And so at the end of the day, I'm not sure which one's bigger, but I can take both of those things that will dominate one way or another. Somebody's going to win. I'm not sure which one. I'll just add those together, chop off their constants. And so really what you put inside the O is this function, n plus m. Does that make a little bit of sense? It's like, I'm not sure which one's bigger. They're both variables. I'm adding the work. That's the answer. Okay? That's how you do it. So that means it's between B or C now. Yeah. Does that part still make sense? You get it? All right. So now we can do space complexity. Let us decide. Let us decide. It is going to be constant space, and let me try to prove that to you. So, all right. Space complexity is how much memory am I using to run this code? How much memory total? So, all right, how many variables am I making here? I've got an A variable, that's an int. I've got a B variable, and it's an int, right? I've got an I variable that I'm making right here. That's an int. And I'm not remaking the I variable, right? Per call or anything. It's just like I'm using that I for the duration of that loop. It's just one I. It's $1, yes? It's $1. It's not being remade or anything. There's no call to new on the heap or anything. That would make things weird. But no, it's just one I. It's being used. And then same for this one. There's one J that's being used. Technically, the I and J could reuse the same place in memory because the I is gone by the time J needs to appear. So the compiler is probably going to be fancy about that, but let's just pretend they're separate because it doesn't matter in the analysis. So at the end of the day, you only need 4 variables, yes? 4 ints to run this code. Does that make sense? So it's like, all right, if you want to count bytes, like four integers, and every integer is 4 bytes long. So that's 16 bytes of memory total. 16 bytes. 16 bytes, no matter what N and M were. So again, that's constant. Yeah, constant space. 0 and space. Yay. And so that leads us to C being the answer. Does that make sense to us? Any questions about how we did that? This is one to definitely practice with. Try to do that. This will prepare you well. Yeah, if we're good, that's more or less what I want to talk about for now. Complexity is going to be in the back of our minds. I'm going to keep using it for the rest of time in this class. But that is, you know, all the main tricks now. That's kind of nice. Just a final anecdote for these slides is a great example of complexity happened a couple years ago in the online version of Grand Theft Auto, the video game. There was like an n-squared algorithm that they were using for something, some sort of verification, some sort of like, I don't know, loading the level. I have no clue what was really going on. Like dealing with the people that you were connected to as you were like about to start your online game. So like the loading screen was, you were stuck on it for a while because they were using an n-squared algorithm to do something, whatever it was. But somebody noticed, like, I don't like how slow this is. Maybe it could be better. Somebody who had the game, they reverse engineered the code. So like they looked into the binary version of the code. They got the assembly version of it out of that, if you know what that is. And they tried to determine like where is this program stuck? Where's the game stuck in its code while I'm waiting for the loading to go away? And so they noticed that, oh, this was an n-squared algorithm that was being used to do something, but there's a better way to do that same thing. There's a linear time way to do it. And so they took the code, they patched the binary, they changed it, because you didn't have the source code anymore, you didn't have like a CPP file or anything. Just like changed the binary version to do it better. And like the load times were more than cut in half. And so that just goes to show, like, we care about these things in real life. Like, money's on the line for this kind of stuff, right? That's kind of cool. And so, sometimes people get really angry when you try and reverse engineer their code and tell them that they're bad. But luckily, that wasn't the case here. Like, the developers, like, they released a patch they did it better. And, like, everybody wins. So, yeah, this is going to be the backbone of everything. Like, if only, right? If only that programmer who made that algorithm for that game remembered their CSCI 41 days, right? So that's where I want you to think about when you become a hotshot programmer somewhere, all right? Any last questions about complexity before we do other things? All right, there's plenty more where that came from. So let's talk about now, we got a lab and a test. So let's do the lab. A lot to talk. Good thing it's a shorter week. I can get all my... What's that? No, we just had 4 days. I didn't have to talk on Monday, so I can get my talking out today. So I have a lot to say. This lab is going to be a little different. It's not like you're just gonna use stuff now. All right. You're also gonna make a searching library. So you're gonna do binary search and linear search from your book. You can just read it off though. I showed you where you could find it. But lab 3, let's look at its code. Start code 41. You'll get it with the gimme command, of course. So you got all these files for your lab 3. And it's mostly just me asking you to play around. So I would like you first to make implement binary search and linear search, because we noticed that linear search was linear time, binary search is logarithmic time. There is a huge difference once you have large numbers, large sizes of arrays and vectors to look through. So I guess let's do the timer class first. So I've made you a timer class, timer.h, that kind of goes over, this is like build a little stopwatch for yourself kind of thing, in the style that I did today. So where were we? You're pretty much going to use this code. And you're going to make a class that wraps around the idea of timing something. Okay? So a timer takes a description of what you're timing, has a start button, stop button, and get back how many seconds were between start and stop, print out the data of our time in a pretty way, stuff like that. And so you got to save these things. Save the time when it started, save the time when it ended. I think you can imagine which are going to be set with those calls. But so that's the header file, and you can do the CPP file from the same thing. So I've already given you that. Do the start and end methods. Do the get seconds elapsed method to give back the number of seconds that have elapsed between the start and stop calls. And then I've also given you print data. So just get practice actually timing something in terms of seconds. So that'll be your timer class that will time something. Somebody's going to call start and end and do some work in between. And then we're going to use that to time our binary search and linear search. So here, as we got binary versus linear.cpp, which has the main function as well. And it's going to use a timer around the things. So you're going to implement both linear search and binary search on vectors. So vector v, and you got a thing that you're looking for, and that thing is called the key. Looking for the key, the needle in the haystack. And you give back the index where you found the thing, -1 if you didn't find it. So implement linear search, you can copy and paste it from your book, more or less. Same with binary search, but hopefully you should try to remember what it is. Yeah. So do linear search, do binary search, implement them. And then this is just using your timer library now. It's we're going to have a bunch of data sorted so that we can also use binary search. And we're going to do a linear search. We're going to make a timer for linear search, start it, stop it, linear search for everything, print out the time that it took to do all that. Same for binary search, start it and stop it. You should see a very stark difference, yes, in terms of how long it took to search for everything with binary search versus linear search, and your timer will prove it. Yeah, and so that's what the autograder is going to be looking for. It's make sure the times are less. But yeah, that's the first one. Just you'll see that binary search is so much better, over twice as fast, probably 10 times as fast, if not more. So that's the first part of the lab. Does that make sense? Just make a little timer class, implement binary search, linear search, watch binary search win. And then the rest of the lab is a bunch of other files. Let's start with the word try. I just want you to get a feel for all the different kinds of things that you could use, all the different data structures that exist, that we're going to be implementing ourselves in this class. So I'm going to have you try out the ones from the C++ standard library. So the ones that have already been implemented. So just like vector, you implemented that. Eventually you're going to implement linked list, but there's a list class in C++. Go and use that. Go and understand it. All right. So that's what I want you to do. So yeah, we're going to learn about a bunch of ADTs, and C++ has implemented a bunch of ADTs. So for example, trylist.cpp, they're all going to look the same. They're all going to look the same. And what I want you to do is use the list type from the C++ standard library and output stuff. So read the file because it's telling you how I want to see the output. But go to the reference page for lists and do all these things. Make a list that holds strings. Use the push operation. There's one called push. Push onto the end, push onto the front. Push this, push that, give me the size of the list, print it out, iterate through the list from beginning to end, print out each value. Use the list, All right, so you'll go to the library page for lists. This is also getting practice for you reading this documentation. That's a very important skill. So go to list, the list class. Here's what it means to be a list. Here's what you can do. There's a push front, there's a push back, stuff like that. You can click on them to see what they do. You got some examples usually. Here's a way to iterate through the list. You could use the range-based for loop as well, but it's probably best to figure out how to use .begin and .end. You can also click, because those are called iterators. Click .begin or something. It should have an example of that being used. But like, make a list of something of the type I'm asking you to do. Run all these things. So go and figure out how to use a list. Does that make sense? The C++ built-in lists, because you're going to be implementing your own. This is an ADT that wraps around essentially the idea of a linked list, which we will be learning about. That and its ADT. Okay. So you're going to do that for a bunch of different ADTs. For a bunch of different ones. Where was I? Here. And so you got that one. There's one called stack. There's one called queue, priority queue, map. They're all there. Try to do it in that order if you can, because they like increase in complexity. And yeah, you're going to be looking at the documentation pages, trying to figure out like, what does it mean? What does it mean to push something to the end? What method is that? Eventually it's like, what was the next one? Stack or something. This one just says push, pop. Interesting words. We'll talk about what those mean. But yeah, when I say print, just print something out on the line by itself. Right? Something like that. But yeah, you'll look at that page. What does it mean to be a stack? What can I do to a stack? That is this one, stack header. That's the stack type. Oh, here are the things I can do to a stack. There really is just a thing called push, a thing called pop. Like, you'll learn how to use those things. All right? And then you'll try to understand them as well, because I'm asking you to do things in a certain order. Hopefully that will be helpful. Because we'll learn about them. So yeah, and I've given you a make file for everything, by the way. So like, if you want to do any of these things, like make binary versus linear, make tri-stack, make tri-queue. If you say make by itself, it's going to compile everything all at once. So you can do that as well. Make tri-priority queue, make tri-stack, all those things. For example, for tri-list, like that's the output. That's what it should look like. Like everything that I ask you to print just on a line by itself. Okay, so you're going to practice using all these different kinds of little ADTs that are baked into C++ because you're eventually going to make them yourselves. Does that make enough sense? Any questions about that? So just go look through the files and then have the documentation page open in a tab and just walk yourself through it. That should do it. I do have also, just in case you've never seen like .begin and .end or anything before, like I did record a little video. It's a while ago, so there's some things that don't apply anymore. But like you can watch that if you want. It goes over the C++ list class if you want some extra help. There's that. Yeah, just try to get all those working. And yeah, you're going to be turning in a lot of files. A lot of files. You're touching a lot of things. So yeah, that is the goal. Let's see. I think that's all that I wanted to say. Especially for this one, you don't want to copy and paste this because I think it like tries to do two separate lines and then it doesn't actually turn in these files. You gotta type it out. It's all one big line. Let's see here. I think that is everything. So yeah, timer stuff, and then these are called container classes. And that will be your lab 3. Questions about that? All right, so there's that. So many things to talk about today. Now we have a test. So this is week 4. Week 6 was when I promised our first midterm. And I'm making good on that promise. So, okay. I'm going to release a midterm 1 module with these 2 pages for now. And I'm going to need to make sure that the extra credit assignment is there too. So you have this now. You've got a midterm 1 info page, and you've got an extra credit assignment page. All right. So with every test, I like to give out an extra credit assignment. But go and read this midterm 1 info page. So this is when we're going to have the midterm, as late as we could possibly have it on week 6. So it will be in class at the start of class on the 18th. All right, so that's the Thursday. So 2 weeks from today, you'll be taking the first midterm in the class. The test itself, you're going to click start and a timer will start ticking down for an hour and a half. All right, so get here. I'm going to have like it go for maybe, let it be, just in case you get here a little late, I'll have it be open for the first hour and 45 minutes of class or something. But like the second you click start, you have an hour and a half to take it. Okay, you'll be cut off if you come late though. All right, there's that. Let's see here. And then here's just a list of topics, like lectures up through week 5. The list, the idea of lists are going to be the last topic that'll hit hard. Some of these labs, like lab 3, I don't know if it's going to be due. I don't remember the due date. Lab 3, may have been nice to you and have it due after the midterm, but I'm going to test you on it. All right. So it might be useful to do it first. Syllabic readings up to and including lists. So just read all this stuff. Like here's a list of topics you should understand. All right. Lists are going to be the most recent thing that we talk about. So I'll ask you like more simple questions about lists. I'm not going to hit those super hard because you won't have had a lab turned in on those or anything. But that's going to be the goal. And that is like what it's going to be on. All right. And then the format of the test is as follows. So I don't know what you did in your CSCI 40 class or equivalent, but once you get to a 4-year college, you're going to be taking tests in a large room on paper. All right. If you have not yet done that, this is going to be you doing that. All right. Once you get to like, once you go and take an interview somewhere, like they're going to ask you to write code on a whiteboard without a compiler, all right? So you need to write code without any extra help. That's what you're going to be doing. This is essentially a written test, but it's going to be on the computers, all right? But you cannot navigate away from the test, right? So you're going to have fill-in-the-blank encoding questions on Canvas taken from all these topics, but the test itself is closed book. It's essentially a written test, but you're typing it into Canvas. Okay, that's what's going to happen. So you're going to have Canvas open, like there's going to be a little quiz that is the test itself, and you're going to be typing code into text boxes on Canvas. Does that make sense? That's what's going to happen, and that's all you get. So you cannot like use the documentation pages or anything. You can do the following though. You get one cheat sheet. I let you have one little cheat sheet that is like a printer paper size thing. So you get one 8.5 by 11 side. Double-sided cheat sheet. You can use both sides, that's fine, as long as you handwrite things. You cannot print anything onto that, all right? You must handwrite your cheat sheet, put whatever you want on it. Put every answer in the tiniest writing you could have for every lab you've ever done or something. Whatever you want can go on that cheat sheet, and of course you can have as much scratch paper as you'd like as well, as long as that starts out blank, but nothing else is allowed, all right? No calculators, no going on the internet, except for using Canvas in front of you. We're all going to take it on the big computers as well, so you might want to get practice with using those if you've brought your own laptop from now on. But you're going to be typing stuff and clicking buttons on Canvas, and that is the one page you can be on during the test. Does that make sense? So it's essentially a written test, but it's virtual. All right, you get your cheat sheet though, and that is what you get to use. So here's a sample midterm. You can click on that, and see. Essentially, I'm going to ask you similar kinds of questions. Like that's the last time I taught the class. That's their midterm. You're going to get something pretty much the same, and that at least in terms of difficulty and mostly topics. So that's what you can practice with. But as you take that, as you practice with that, don't use a computer. Like write down your answers or type them up into Notepad or something. Cannot compile it. You don't get any of that. So yeah, that is what the test is going to be about and the logistics of it. And that's how you should practice. Are there any questions about that? Yes. Yes.
Study session for this midterm. If they haven't heard the Discord already, they should be.
Yeah, so definitely respond to that if you're interested in a study session. Those cannot hurt you to go to one of those, right? So that would be great. What else do I want to say? Is there anything at all about the midterm? Yeah. No, I think that's pretty much it. So yeah, it's just like you're gonna be writing code. So you gotta know your C++. With every test, I like to give, and I guess I could do this a little bit later. Let me change the due date of this. With every test, I like to give an extra credit assignment, and this is the only thing that I'll ever have due at midnight for everybody. This will be due the midnight before the test happens, and I think I'm off by one day there. So it'll be the Wednesday, the 17th, when it will be due. So extra credit assignments, any extensions that I've given you in the class do not apply to exams or extra credit. So this is due at midnight, the day before the test comes out for everybody. And there are no late submissions, even if you have technical difficulties. You should have turned it in sooner. So, all right, if you would like to do it, this is worth up to 2.5% extra credit on top of your final grade in the class. Make sure that you submit on time or early, because like if you have problems, I'm still not accepting it, all right? No late submissions at all for this. What you can do, if you would like the extra credit, is to make a review video. All right, so this is me kind of forcing you to study. It's great, right? It's a win-win. And you'll post it down here. It's like a little discussion on Canvas so everybody can see it. It's like your peers get to enjoy some extra study material as well. That's perfect. So win-win-win, all right? So just like upload a video as I do for my lectures. You don't have to like edit it, make it pretty. That's fine. But like record yourself. Record yourself on your screen or something. And I can help you with that if you need any help with that. But here are like the hard requirements for your review video if you'd like to do it. Definitely, like, you need to review stuff, right? So come up with some examples of things that will be on the exam. Be as creative and fancy as you'd like. And just kind of pretend to be a teacher, right? Go through the examples and just be like, here's the thing, here's the answer. Here's the thing, here's the answer. Like, go through it, right? Be a teacher. Otherwise, it's not helpful. That's not really a review. If you want just half of the points, you make a 10-minute video, at least 10 minutes long, going over some stuff. If you want the full 2.5%, please make at least a 20-minute video where you go over some examples, go through some problems, solve them, stuff like that. Does that make sense? That's what I want. And just to be very clear, right? This is extra credit. It's got to be extra. So you can't go over something that you've already done. So like you got to make something brand new to receive credit. That is extra credit, right? So make some new code, right? Create new slides, draw new diagrams, stuff like that. Don't read my slides. I will not give you credit for that. Don't go over an answer for a lab that you've done. That's not extra. Does that make sense? Do something extra to get extra credit. If you have any questions about your idea, before you do it, you can contact me and I can tell you if it's a good idea or not, if I'll give you credit. Most reasonable ideas I will give you credit for, right? As long as you're not just like being lazy and going over something you've already done or that I have done. So yeah, I think that's all that I want to say. I can help you record if you need to. I use this program called OBS. Zoom itself also will let you record, but all that I need is you to click reply and upload your file somehow. And then we can all see it and I can give you credit and your peers can use it to help them study. So I think that's all that I want to say. This is due the midnight before the test comes out. So the 17th at 11:59 p.m. Any questions about this assignment? So yeah, definitely. I think it's a great way to help yourself study. Like, you know that, like, if you guys ever become a teacher, you will learn very quickly that you really you make sure that you understand things before you give a lecture. Like it really helps you figure it out. So it's a useful process. So yeah, those are the things that I want to give you. Eventually, this is where you'll come on this module to take the midterm. You click there, and you click start. All right, and that's how it'll work. And I think that's pretty much all that I wanted to say for the day. I think I'm finally done talking. Are there any questions about any of that? We did it. So yeah, we're all going to take the test in this room on the big computers. And I think that's all that I wanted to say.